This module summarizes the final conclusions and findings from the project that we have been looking at for the structural fire engineering and design of Speedcore for fire resistance. In summary, we conducted extensive research to evaluate the stability and strength of composite plate shear walls and concrete filled tubes under fire loading. Experimental studies were conducted for the composite plate shear walls or Speedcore. Detailed finite element models and fiber-based models were developed and benchmarked using experimental data for both the composite walls and columns. Using these benchmark models, detailed parametric studies were conducted considering material, geometric, and gravity loading parameters for both these composite walls and columns. The results from all the experimental investigations, numerical investigations, and parametric studies were used to develop strength degradation equations for these composite columns and walls under fire loading. Fire resistance rating equations were also proposed for composite walls to be used along with prescriptive methods. We also developed tools for conducting performance-based design of these composite walls and columns with a graphical user interface for efficient pre-processing and post-processing of the type that the engineer can follow and direct. A rational vent hole design method was also developed for composite walls. In terms of conclusions and major findings, we find that increasing the wall thickness improves the fire resistance rating of the Speedcore or composite walls substantially. Experimental and numerical observations showed that local buckling is limited to occur between the tie bars. Increasing the wall slenderness or the story height of the wall divided by its thickness has a detrimental effect on the fire resistance rating and strength of walls at elevated temperatures. Generally, for a two-sided fire scenario where the heating is applied on both steel plates, on both exterior steel plates, the fire resistance rating of these composite walls is very high. When there is a one-sided heating, that means that the fire exposure is applied on only one side, then you have to demarcate between the slenderness ratio of the wall, which is defined by the story height divided by wall thickness. When this slenderness ratio is less than 20, then you get pretty long fire resistance from these walls because of the contribution of the material strength, both the concrete and the steel, on the unheated side. However, when the slenderness ratio becomes greater than 20, which is quite remarkable and doesn't generally happen in typical construction, but if the slenderness ratio is greater than 20, then you can have lower fire resistance due to the generation of a thermal gradient, which results in global buckling. In such cases, there is a need for fire protection, at least on the side that may be exposed to fire. Vent holes can be designed using the developed method, and we generally recommend at least 2 vent holes along the height of each story. In this case, in the final conclusions, looking at composite columns, we generally find that non-compact or slender sections have lower fire resistance rating. The fire resistance decreases with reducing concrete strength, and fire protection of the steel tube can generally increase the fire resistance rating by a significant amount. Simple design equations were proposed to calculate the axial load capacity Pn at elevated temperature T for both the composite walls and columns. And this simple equation is in the same format that you typically see in Appendix 4 of AISC 360 or the specification. For example, for walls, the equation is 0.32 raised to the power Pno as a function of temperature divided by Pe as a function of temperature raised to the power 0.3, and that is multiplied by Pnot. In these equations, Pnot is the section axial load capacity at the elevated temperature, and PET is the Euler buckling load for the column or the wall at that same elevated temperature. A similar equation for concrete filled tubes is also provided for calculating the strength using a simple equation. Finally, a fire resistance rating equation is also provided for unprotected composite plate shear walls or Speedcore. In this, R is the fire resistance rating in hours, and it depends directly on the applied gravity loading, Pu divided by Tn, the wall slenderness ratio, H over Tw, and the thickness of the wall, Tw itself. As you can see, the fire resistance rating increases with increasing the thickness of the wall. It decreases with the wall slenderness, H over Tw, and it also reduces with increasing gravity loading. So those are the final conclusions associated with this particular project, and they're provided in, of course, more detail in the report, which I highly recommend for you to read, and future publications that we'll have on this topic. This slide lists some of the references that we have cited during the presentation. Of course, there are more references that are available in the report that we have cited. But just in the presentation itself, these are some of the references that we've cited, and we wanted to make sure to include them in this section. If you have been following along for all this time throughout the various modules of the presentation, then I want to thank you for your attention, and I want to acknowledge that this is the end of the presentation that we've recorded in order to present the project report for the structural fire engineering and design of filled composite plate shear walls, also referred to as Speedcore. My name is Amit Varma, and on behalf of my entire team from Purdue University, I want to thank you for your attention and your interest in this topic.